I'm mostly a theorist, as you probably already heard about, and I rely on experimentalists to kind of look at things and try to work with experimentalists on things. So just with that in mind, keep it real. So what is nano? I think it's in the popular vernacular nowadays. People use the word without thought. There's a couple of nano things that we know about here. The Nano, the Tata Nano, that little car there. Maybe I'll get a chance to see it next week. I'll be in India. But that's hardly what we think of in the technological sense. Maybe that's about a cubic meter, a meter on each side, more or less. Or the Apple Nano device might be a cubic centimeter, a little bit smaller, but that's not even close to what we're talking about. What we talk about when we say nano, we usually think of nanometer. Nanotechnology should be working on some nanometer scale of the technology. So that's a billionth of a meter. So a decimal point with 8 zeros and a 1 past it, that's a nanometer. And you want to look up something, all things nanotechnology, you can go to this website. It's a fairly popular site. There's something for everybody on that site. And of course, there's a nanomania now, and nanomania means everybody is kind of putting up sites, putting up journals, conferences of all types. They're all running into each other. I have a couple of titles here. Nano Letter's pretty popular, Nanophotonics, Nano Today, and so on down the line. There's lots of them. And what I have here are two allotropes of carbon, basically two forms of carbon. This one here is called a buckyball, or Buckminster fullerene in its full form. And this one here is a carbon nanotube. Basically take graphite or graphene and you roll it around and you get this kind of rolled up cylinder here. Both of these are on the scale of nano. So it's indicative of the kinds of things that you want to do in the nano world. The subject of this talk, I was trying to, there's a bunch of words in there. I think I've explained nano, but there's a few other words in that title that are really kind of odd. First of all, quantum description. I'll say a little bit more about this in following. When I say quantum, what I really want to do is talk about the electrons and the electron tunneling from one metal into another. And the sandwich here, this will come up again, basically is a metal and a metal with an insulator in between. So normally you wouldn't get a current passing through there, but if that gets small enough, that insulator thickness, then you can get tunneling. This is so-called MIM structure, metal insulator metal. Think of it that way. And also, I'm going to examine unusual electromagnetic scattering properties from these MIM structures. So that's going to be the way we will probe the structures and understand how their quantum properties work. And if you want to think of metals, aren't very good at optics. Normally you don't take a piece of metal and do some optics with it. But in fact, if you make the metal small enough, and this Lycurgus cup, actually made in the 3rd and 4th century AD in Rome, the properties of this cup here, so-called dichroic, are because of nanoparticles of metal that are put inside that cup. It's really quite a beautiful cup. It's got this this cage around it, and then the actual glass is put in here. So the Romans mastered this technology. What is it made of? It's made of silver and gold. That's all it's made. Yet it has these beautiful colors. Why is it dichroic? This here is the lighting from the front, so it's reflected off of it. It looks green in color. In this one, it's actually lit from behind, and so it has a red color. So depending on how you light this cup, it has a different, it shows a different color. So that means dichroic, or two colors. Plasmonics, that's another word that appeared, nanoplasmonic. We know the nano part. What's the plasmonics? All you have to think of in terms of plasmonics is metals. So it usually or always means we're going to talk about the electrons moving through the metal. They move more or less freely through the metals. And so we talk about the electron density dynamics in the materials, and that's a word that we've coined for that oscillation, that motion, driven by electromagnetic fields is plasmons, or plasmonics is the field. So we could treat it as a particle or a wave in a quantum context. I'm not going to treat the plasmons per se. I'm going to treat the electron motions and not necessarily the plasmonic. And we'll see how that works into our theory. So my motivation for this research, it's an entirely new technology for energy harvesting. I was sort of going through the literature. I noticed some papers on these so-called MIM diodes, and I wondered exactly how they worked. And there was some discussion in the literature that maybe we could use these for energy harvesting. Instead of photovoltaics, we would use MIM diodes. There's always a possibility for that. And the other interesting thing is it relies on the quantum properties of the device. It's not a classical characteristic of it. And this has to happen on the nano scale. So that gave us an opportunity to discover. So why follow this sort of uncertain direction? When I started this, I had no idea that it was going to lead to anything. And actually, I'm still not sure exactly what it's going to lead to. We have to perform some new experiments, but it's a challenge. So we could maybe harness a new source of energy. And I really kind of relate it to mountain climbing, which you saw that first slide of Dayton there. No, it wasn't Dayton. It was the Adirondacks. But you saw that first slide. That's one of my hobbies is to climb, actually hiking. And you want to be able to find out new information, maybe go to a path that people have not taken before. Maybe many people have been to the mountain, but they haven't taken this particular route up. And this would be one. So I sort of take that analogy of climbing a mountain. Also, the other analogy with Robert Frost, the road less traveled. A lot of people are traveling the photovoltaic route, and they're putting nanotechnology into that aspect of technology. But this one has not been very well studied at all, and I think it deserves a chance to be studied. So the payoff could be cheap new energy source for the world. So back to that analogy at the beginning, how low can we go? What's the limits? There was a talk by Richard Feynman in 1959, basically right after integrated circuitry had been invented, hardly in our consciousness at that time. There's a couple of things I want to note about this slide here. One is the date, December 29th, 1959. He was giving this at an American Physical Society meeting, and I wondered to myself, today, do we hold meetings just before New Year? Between Christmas and New Year? Who does that nowadays? It's not done. Well, back in 1959, I think it was normal to have these kinds of meetings in that time where not much else was being done. The other thing that he said, well, look, there's really plenty of room at the bottom. That was the title of his talk, plenty of room at the bottom. He saw no limits to miniaturizing electronic circuitry. And he talked about that at length, putting the encyclopedia on the head of a pin. Okay, in principle we could do it. In practice, we don't have the technology yet. Then he also mentioned, well, we have to read it once we put it there. So we need to have the characterization tools to do that. And he also said, well, even there's no limit. I mean, electron microscopes weren't that good at that time, but he said it could get much better and some of the roadblocks could be overcome. And he was right about all of that. So in a sense, he was prescient. People like to point back to this as kind of a beginning for nanotechnology, but I think in the history of nanotechnology, it really didn't carry it through. It wasn't in our consciousness. It's kind of an afterthought people point to because he was such an iconic figure. Well, the real things, after 55 years, we are now reaching the limits. We're now getting to critical dimensions for structures like the MIM structures, which are less than a nanometer. We're able to put down films with controlled thicknesses that are less than a nanometer. Now we're reaching the limits. I mean, there's how much further can you go? And now you have to start introducing real quantum mechanics in order to understand these. And that's where we were coming from, trying to get to these boundaries of physics. So first thing is quantum tunneling theory. It's been around for a long time. Radioactivity was, of course, late 19th, early 20th century from the Curies and Becquerel. In 1928, alpha decay was kind of explained theoretically as you have this alpha particle. An alpha particle is just a helium nucleus. And this alpha particle is thought of as being trapped inside this nucleus. And of course, because it's a positively charged thing, there's going to be repulsion when it gets to the outside, but it has to get through this barrier here. And the theory kind of explained all of these properties of it for the first time. Soon after that, the physicists of the era realized this doesn't just apply to nuclear physics. It's not just a one-time thing. This applies to a whole host of phenomena. So things like molecular spectra, semiconductor, solid-state electronics, it kind of grew out of this idea that there's a quantum phenomena here. Other things like superconducting devices that people had developed and used, all kinds of systems. I showed here one, this isn't a grape thing, it's an actual tip of a tungsten. This nanoscale systems like a scanning tunneling microscope, which was developed in the 1980s for the first time, also works on the same principle. And you have tunneling between this tungsten tip here and whatever surface that you have there, and it feeds on the electron clouds that you have around here. So it's very indicative. Actually, this scanning tunneling microscope is one of the best tools we have for highest resolution for looking at surfaces of samples. So it really is quite a good. Here's another cartoon that I put up just to bring home the difference between classical and quantum. So in classical physics, if a particle has a certain kinetic energy, a certain velocity in other words, and it just can't get, the barrier has too much a potential in order to get over, what happens? It slows down, it stops, and then it turns around. It can never get over that barrier. In quantum mechanics, this cartoon here is supposed to show wave comes in, it interacts with the barrier, but something can leak through. There's an evanescent field that kind of pulls through. Some of the particle can go through, and some of it can be reflected. And on the average, there'll be a bit of the particles that will get through, even though the kinetic energy of that particle is below the barrier. Because it's a wave, it can see through that barrier there. So that's the difference, and it's now back to the MIM. It's the same sort of thing. Here's a structure that people make for these MIM diodes. You have an antenna, basically a dipole antenna, with two metal strips here, and those two metals can be different. That's why one is yellow and one is kind of a pinkish color. And then between them, you have an insulator, so they're not short-circuited between them. And that's where the MIM diode, so the energy has to get from here down into the diode area. And this structure here where the MIM is given by this diagram here. So you have some electrons here, which are filling up the metal to a certain level here, that EF, which is called the Fermi level. Then you have the insulator, which has a barrier, which we can calculate by parameters that are given in the literature. So there's no guesswork here, no extra parameters you have to invent. And then you can apply a voltage to this as well and lower that barrier. But also the electromagnetic radiation applies that voltage. So you get this tunneling current because of the sloshing around of electrons as this voltage is changed back and forth. When they slosh around, there is an asymmetry in that. And so there's an extra DC. Are you, am I over time?
I don't have a hook.
Oh, okay. 20 minutes, really? No, can't be. Impossible. We started at least 35.
It is Professor Haus, right?
Yes, okay. Quantum tunneling is a conductivity, and conductivity is basically given by Ohm's law type thing here. Here you have a current density and a field, electric field. That electric field, when the current flows, can be described by a conductivity. Here I have it dependent on the conductivity as a field-dependent quantity. So in general, we get some nonlinear terms, like Peter's work, which can give us further insight, a kind of nonlinear signature of the quantum process. And that's really what we want to do. So once we have this conductivity, we can put that into our electromagnetic scattering calculations. Yeah, with light, it doesn't go over the barrier in our picture. It kind of changes the barrier, what they call photon-assisted tunneling. So it's like it adds a voltage bias to this, and that changes the current. The more light you have, the higher the current in general. So you can measure this current and measure and compare that against the theory. And it depends on how strong the electromagnetic field is, and that's hidden in this parameter here. And this here, this parameter is just the energy of a photon. That's the parameters. Metals are interesting from an electromagnetic point of view. Mentioned this free electron and this collective motion of the plasmons. And the idea of the plasmon, you think of a plasma, plasma is a neutral gas of ions and electrons. Well, that's what a metal is, except we're not doing it at high temperature. We're not trying to do fusion of any kind. But it's really just like a plasma. And when you have that below a certain frequency, called the plasma frequency, the dielectric constant is negative. And so you get this real part that's negative. The bad part is you got an imaginary part, which is losses, absorption, which is always there. And you always got to deal with that. So working one against the other, that's what we do. If you take a rod-shaped thing, you can get very strong fields at the peaks, just like Benjamin Franklin did in his little experiment with the kite and developed the concepts for harnessing lightning and making buildings safer. Same sort of thing here. We got this lightning rod effect that you get from these things when an applied field. And the field can be quite a bit stronger, but it even gets stronger if you put two rods together like this. And then between those two rods, they'll blow this area up and you get a very strong field, which can be 3 orders of magnitude larger than you would get from the applied field alone. So that's what enhances our nonlinear effects. And we can get really huge nonlinear effects out of this. Types of effects we can get: second harmonic or third harmonic generation. That is 2 photons in, 1 photon of twice the energy out. Second harmonic generation. Or third harmonic generation, 3 photons in, 1 photon out. Those are the things. These will really be what we'll look for when we try to do our experiments. Those experiments are being designed now. This is just showing the quantum effect. Classical. In classical physics, no matter how close those two get to each other, the field keeps going up. It goes off to infinity. That's classic. But once you get below a nanometer, the quantum effects start to, and that introduces a conductivity in this space in here. And that conductivity quenches the field. So instead of going up and up and up, shown here, instead of that, you get a peak. And then for smaller, this is 1 nanometer here. Below a nanometer, it starts to quench down. And this is just cross sections of that. The solid lines are the quantum, so it goes up. The solid and dashed are together. Here it falls below at around 0.6 nanometers, and then it continues to drop off. Nonlinear effects also are there. I'm not going to belabor this point. Classical, again, gets bigger and bigger. We already saw the low field case, the linear. But non-linearly, if you add a high power laser to it, 1 gigawatt, 5 gigawatts, you see definite changes. And that was discussed in some theoretical papers, and we can calculate these things with a very simple calculation. So it brings down, what do we really know when we get below a nanometer? we treat the surfaces as though they're hard surfaces and fixed. But we know from detailed quantum calculations that the electrons are kind of flowing out from the nuclei, and it gives you a extra skin around the structure. So instead of treating the free electrons and the bound electrons as having the same boundary, we treat the free electrons and the bound electrons as having a little bit different, by about 2 angstroms, that sort of difference. And that comes out of calculations, detailed calculations. The linear properties actually aren't much different when we take the shell or without, but the nonlinear properties can be orders of magnitude different. So this could be the distinguishing factor between having the skin, trying to take that into account, and having just a hard boundary that's identical for both. So I think that's it. You have these quantum conductivities. We have some nonlinear effects. Been doing inserting those into our electromagnetic calculations, and we're still working on this because actually mountains don't give up their summits very easily. Some of our collaborators, Peter Powers, of course, here. Li did her master's thesis on this, and Kong Deng Kate worked on some metal systems, nonlinear optics. And I spent a year on my sabbatical in Huntsville, Alabama with Mike Scalora, and I worked with Domenico and Antonella on the electromagnetic calculation. So they're really the experts at that. So thank you very much.